We've all heard, if you've done physics, of F equals ma. It's one of those very famous equations that Isaac Newton formulated. But where does this equation come from, and how can we calculate what this is? Well, if we look at this closely, what we can say, well, if we give a scenario, if I have a particle and it has a change in velocity, dv, but it has a given mass, so m, and it's going to be travelling over a given time, right? If we look at this, we know in everyday life, when we have a change in velocity, we experience a force, something pushing us back into our seats when we're accelerating in a car, or whether you're on a fairground ride or anything like that. So what we can say here is we can use momentum to work out what the force is. If we go down here, we can say that P, which stands for momentum, minus P sub 2 over a change in, over a given time. So this change in momentum over time is directly proportional to a force that we experience. We know that P is equal to mv, mass times velocity. If we put that in here, we could say the mv, which is actually our final momentum, so this should be 2 and this should be 1, minus our initial momentum, where the u is just the initial velocity, over a given time, is directly proportional to some force. So we can actually factorize here, we can factorize m out. So m times v minus u divided by t is directly proportional to a force. So if we look at this, we can actually see, well, v minus u, what was v minus u? Well, v minus u is equal to delta v, so that's dt. We know that acceleration is equal to dv by dt. It's the change in velocity over a given time, or the change in time. So if we replace this t and delta v, because we know that m is now dv over dt, which is directly proportional to f, where dv over dt is what this is, because this is the change in velocity over time. So if we bring it up here, we can then say that ma, because that's the acceleration, because we've worked it out, is directly proportional to a force that we experience. So we know if we're doing in proportions, we know there's a constant in there. So ma equals f, kma, sorry, is equal to f. So f equals to kma. K is what's known as an arbitrary constant. It's a constant that doesn't really affect the equation very much until you get to really high speeds. What K is actually just the equation that relates to the relativistic effects as you get closer to light speed, which is just 1 over the root of 1 minus v squared over c squared. If you take if you've done relativity or had a look into special relativity, then you'll know what this formula means, and this is what this is. Isaac Newton, when he calculated this, didn't know about this equation, but he knew that there was some constant. But at the time, when he did tests on this, and he times the mass by the acceleration to work out what force he wanted in newtons, he found out that this constant here didn't really affect the results. And he thought it was an arbitrary constant, which it is, but only at low speeds. As you get closer to light, this means something. And the k is just gamma, which is equal to this. So, getting rid of this k then, because it doesn't matter at low speeds, because it's literally almost 1, F is just equal to ma. So if you've ever wondered where that equation comes from, now you know. So just to recap, we know that if we have a particle, let's say a car or a bus, has a change in velocity over a time, we experience a force, but we want to work out that force. So if we take the mass of the particle, and we know the mass times the velocity is the momentum, then the change in momentum over a given time gives us a force. So we put that in here in terms of mv, which is directly proportional to F. And so if we factorise them out, which we did, we get v minus u, which is the change in velocity, and that gave us this equation, because we know that this acceleration is dv over dt, and this is a change in velocity over a change in time, and so we replace this v minus u over t with dv dt. dv dt is acceleration, so if we go back up here, ma is directly proportional to f, so kma equals f, so f equals kma, and k is an arbitrary constant where this formula only applies as you get bigger. And it's actually quite easy to see. If this is the speed of light and this is your velocity, you know, if you do this on the calculator, it's quite easy to see then that at day-to-day speeds this is pathetically small. It's 1. It's slightly more than 1 if you're going at a velocity, but it's nothing really that's going to affect your equations if you just use F equals ma. So the equation is just F equals ma, which everyone knows.